Okay, so we are going to pick up where we left off yesterday. This unit Unit 9, it really is talking about thermodynamic favorability. And in the last section, we looked at delta G, delta H, and delta S, and combinations therein, and studied whether or not reactions were going to be favorable or not. Because remember, just because we put A and B together doesn't mean that anything's going to happen. Now, electrochemistry, what we're going to do here is we're going to pick up where we left off yesterday, and I can kind of see why they put electrochemistry in this unit. Because the way you build an electrochemical reaction is by focusing on thermodynamic favorability and voltage to do it. And so that kind of comes from what we did in the last section. Now, yesterday we looked at these half reactions. That's what we're going to focus on from here on out, where you have a reduction reaction, an oxidation reaction, and you put them together and you get this overall reaction. The driving force for this, as you can see, tin is losing electrons and it is giving them to iron, which is gaining electrons. And that transfer of electrons, there you go. This might start to make you think of a battery, and you would be right. So we transfer electrons from one metal, the other metal receives it, and that flow of electrons occurs in a wire, and we're going to study these cells in a little bit. But first, let's start with the very basics. We're going to look at a reaction where we have zinc and copper. We're going to take zinc metal in a solution of copper sulfate, and we are going to watch as copper solid collects on the zinc metal. So you guys studied these. This was in pre-AP, right? These are single replacement reactions. And let's look at this video, and you'll see how this works.
When a strip of zinc metal is immersed in an aqueous copper 2 sulfate solution, electrons are transferred from zinc to the copper 2 ions. Copper metal deposits on the zinc strip and collects at the bottom of the flask. Zinc atoms are oxidized to zinc 2 ions, which enter the solution. This spontaneous oxidation-reduction reaction is summarized in the chemical equation shown.
All right, so I'm going to stop that because I didn't really get a chance to move that over. There we go. All right, so you can see I've put my zinc metal in the copper sulfate solution, and the zinc is losing electrons. It's coming off, and I'm going to show you a really cool animation of this in a minute, and that is being received by the copper ions in the salt, right, because I've got these copper ions in solution, and when that happens I make copper solid. So I'm getting a transfer of electrons from zinc to the copper. All right, that's our driving force. That's why this reaction works. Now, when we look at this, we can see that zinc is 0 here and it's +2 here. So that the zinc is being oxidized, and copper, which is a +2 here, is now a 0. It is being reduced. So that's how we're going to do that. That's how you can determine which is being oxidized and which is being reduced. Now, when a strip of copper metal is placed in a zinc sulfate reaction, this does not take place. Remember, we learned in the last section that if a reaction is favorable in this direction, it is unfavorable in the reverse. And so this is because zinc loses electrons more readily than copper does. And we're going to, don't worry about the hints, we're going to talk about how we determine this numerically in a minute. Now, in a voltaic or galvanic cell, the transfer of electrons takes place through an external pathway rather than directly between reactants present in the same reaction vessel. So if we go back to our video, right, this is one reaction vessel and the electron transfer is occurring here. But what we're going to focus on now is, what if we create a system where the electrons are not flowing in the solution, they're actually going to be being transferred externally. So let's look at this next.
The spontaneous copper-zinc oxidation-reduction reaction can be made to yield useful electrical work by incorporating it in a voltaic cell. The zinc electrode is immersed in a solution of zinc sulfate. The copper electrode is immersed in a solution of copper 2 sulfate. No current flows through the light bulb because the electrical circuit is not complete. To complete the electrical circuit, we add a tubular bridge filled with aqueous sodium sulfate solution with a porous plug on each end. We now have a complete circuit and current flows.
Now this is really important. I want to stop the video here because you need to remember that having the metals, which, where you can have the chemistry occur, is important. But because we are forming ions here that weren't here before, and we are losing ions that were here, that has to be taken care of through this salt bridge. And so unless we have the salt bridge, the current is not going to flow.
When we replace the light bulb with a voltmeter, we find that the cell has a potential or voltage of 1.1 volts. The copper electrode is the positive electrode, and the zinc electrode is the negative electrode. As the cell reaction proceeds, zinc atoms of the zinc electrode lose electrons and move into the solution as zinc ions. At the same time, copper 2 ions acquire electrons at the copper electrode and form copper metal. The reaction in the left-hand compartment is oxidation of zinc. The electrode at which oxidation occurs is called the anode. The reaction in the right-hand compartment is reduction of copper. The electrode at which reduction occurs is called the cathode. Electrons flow from the anode to the cathode through the external circuit. To maintain electrical neutrality in the two cell compartments, ions must move through the salt bridge. In summary, remember that in a voltaic cell, the anode at which oxidation occurs is the negative electrode. The cathode at which reduction occurs is the positive electrode. Electrons flow through the external circuit from anode to cathode.
All right, so we're going to have to memorize that system, so let's break it down in more detail. Okay, so electrons flowing through a wire. Remember, we saw the electrons flowing through that wire, and ions moving in solution both constitute an electrical current. Remember, we have to have both. This flow of electrical charge can be used to accomplish electrical work. If the two solid metals connected by the external circuit are called the electrodes, oxidation occurs at the anode, and the way to remember this, I'm going to circle. O and A are both vowels. The vowels are together. And reduction occurs at the cathode. Reduction and cathode both start with consonants. Consonants, I guess that's how you spell that, I'm not sure. And so those stay together. As the galvanic cell runs over time, the mass of the anode decreases, because remember, metal is turning into ions and going in solution, because the atoms of the metal are going into solution and becoming aqueous. As the galvanic cell runs over time, the mass of the cathode increases, because the aqueous solutions, ions of the metal, are converted into atoms and deposit on the surface. So what I'm going to do, so the half reactions we learned, Zn2 plus 2 electrons, and this one is copper 2 plus 2 electrons give copper. So we've got zinc leaving the electrode and going into solution. We've got copper taking those electrons that zinc gave up and picking those up and becoming deposited on the cathode. Now, if I take these two reactions, we're going to cross out our electrons. The overall reaction that we get is this. Now, what I want to do next is I want to show you a really interesting simulation about how this works. So let's look at what's happening at the zinc node, right? Okay, so here's zinc. The green are the electrons, and the large, you're going to see a large sphere, is the actual solid. And so if I hit this simulation, what's happening, watch, the zinc is spitting out the electrons and coming out as an ion. You can tell that because the radius of the zinc is shrunk. Remember, cations have a smaller radius than the actual metal does, right? So that's what's happening. I'm going to play that again. There's your solid, your zinc metal with its electrons. It's going to spit those 2 electrons out. That's going to end up going on the wire, which is going to make its way to the copper, and I've spit out the zinc 2+ cation. All right. Okay. Oops, sorry. All right, let's look at what's happening on the copper side of things, the cathode. All right, so here are the copper, this is the copper, piece of copper that's sitting in solution. But this time, remember, this is surrounded by copper sulfate solution. So I've got copper 2+ ions in solution. So those electrons are going to come around in the wire. There's those electrons from the zinc. That copper 2+ small cation is going to pick those things up and deposit. See how they're becoming copper solid. So let's play that one more time. I've got copper 2+ ions. There it is. There are the electrons from the zinc coming up around, and those copper ions are going to pick up those electrons and become copper metal, and then more and more copper metal is going to sit on that electrode. So I'm going to stop the video here because what we want to do is very slowly and very carefully diagram this whole system for us to fully understand the cell.